2-1 homomorphism. This thing SU2 to SO3. So we have now examples of both isomorphisms and homomorphisms. Now I want to go into basic definitions of things like subgroups. So my plan is first to go into general ideas, okay, hopefully with lots of examples. If you want more examples, just ask, and eventually settle down to discussing in the finite case, particularly the permutation group, in a fairly complete way. So I will do the representation theory of the permutation group to the extent that time permits, okay? And then we will go into continuous groups. Okay? Continuous means what they call Lie groups. So that way I will have hopefully a balanced presentation of both finite groups and Lie groups. So what is a subgroup? Well, the definition is quite obvious. Okay? A subgroup H of a group G is a subset, okay, which is closed, which is itself a group. Okay, under the group laws of G. So, okay, H1 H2 is in H, implies the product is in H. Okay, H1 Hi inverse is in H, and then identity is in H. Okay, you are not allowed to introduce new multiplication rules in H. Okay? You can sometimes do it, but that will not be called a subgroup. So under the same multiplication laws you are encountering in G, H is closed. H is a closed set. So let us look at examples. Okay. Let me look, for example, on the group S3. Okay. S3 is permutations on 3 objects, okay, and this has 3 okay, S2 subgroups, right, namely permuting, okay, consisting of identity and the permutation of ing, okay, and so just transposing 2 of the elements. Okay. So there are 3 such subgroups, all of which are S2. Okay. So because they are permutations isomorphic to S2, and they are clearly isomorphic. Let me look at a slightly more complicated example. Let me look at SO3. Rotations in 3 dimensions. This has an infinite number of SO2 subgroups. What can that be? Can you get? Okay. What may be the subgroups? Can you tell? Around an axis, fixed axis. Yeah. So, one particular, okay, one such will be rotations around an axis n. So, you take all rotations around that axis, that is and it is simply like a rotation in a plane, okay, namely the plane perpendicular to this axis, and also clearly they are all isomorphic, okay, all isomorphic. The map, okay, the isomorphism is since, okay, rotation by theta around n, okay, to the rotation by the same angle theta around m, okay, to rotation by same angle theta around m. There is clearly an isomorphism map, but this group has some other subgroups which are of great interest. SO3 has several discrete subgroups, okay, has I may not remember all of them, the tetrahedral, icosahedral, or like what is it called, symmetry, so what they call Platonic figures, no? So it has example will be the tetrahedral group. What does it consist of? So this consists of 4 elements, 1 1 1 1, determinant must be minus 1 1, no, determinant must be plus 1, so it will be minus 1 1 minus 1. Then you have what? Minus 1 minus 1. There is one more possibility. Minus 1 minus 1 1. Okay. This one thing. Okay. 4 element group. This is the symmetry. Some of you know this is the symmetry of the molecule C2H4. If you know this molecule, carbon I think. Ethylene, I think. So these are rotations by pi. This is nothing. This is rotations by pi around 3 perpendicular axes. Okay. This one, and this one. In the ethylene molecule, for example, if I rotate this around this axis by pi, you get back the same figure. If I rotate around this by pi, you get the same figure. And if you rotate by pi around this axis, you get the same figure. So this is the symmetry of this ethylene molecule, but there are other much more complicated things. What is it called? I am not remembering all the name. This icosahedral, dodecahedral, there is some more things. There is also some funny group consisting of a rotation around one axis and a reflection. There is a rotation. Okay. It also has another subgroup, okay, which is not, I don't know what it is called. It consists of all rotations around third axis, let us say. So it will be cos theta, sin theta, minus sin theta cos theta 0. So it is rotating around third axis, not 0, 1. Then, so I am rotating around the third axis, then I rotate by pi around the perpendicular axis. So I take this rotation by pi. So it will be minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So I rotate around this and I rotate by pi around this axis. This also comes for some molecule. I am trying to remember what, oh yeah, if you take a molecule like this with some identical things here, say NN, I don't know what this N is. This one, if I rotate around this axis, doesn't change. If I take here, I rotate by pi, like this, nothing happens. So for that the symmetry group, so-called symmetry group is this. So there are other things, never mind. Now, but I want to look as an example what happens with SU2. And I want to just check, all these things have counterparts in SU2, but here most interesting thing, maybe we have time to look at later, that this T4, the dihedral group, T4 Hamilton, becomes something very interesting, so called binary dihedral group. Which is a non-abelian group, that is, it is not commutative, I mean elements of the group do not commute, it is called D star 8, and I will give you the elements, consists of 1 plus minus 1 and plus minus I tau I. I is 1, 2, 3. These are Pauli matrices. You can check that these are in SU2, and there are 8 elements here. Okay. So this one, if I take this group and quotient this by, that is, you take the isomorphism map, homomorphism map from SU2 to SO3, which I gave you, and see what happens here. It becomes that T4 group. Okay. And it turns out that this has some role to play in chemistry. For example, the degeneracy of the spectrum of the ethylene molecule in its ground state, this group governs it. Okay. Now let me give other examples. Yeah. Okay. 4. Clearly, real orthogonal matrices are unitary. That's obvious, right? So immediately we find an inclusion like ON is contained in UN. Okay. But in fact, then some obvious things will be things like U2 is contained in, U3 is contained in. You can easily read off these things. Okay. For example, in the 3 by 3 matrices of U3, this U2 will be the 2 by 2 block. It is not unique. You can take any 2 by 2 block or any similarity transformation of that. Okay. But there is something more non-familiar, for example, namely, this is also true, that if you take UN, this is a subgroup of SO2N. This is somewhat this is actually quite interesting. Not let me show it to you. Okay. This is quite interesting, and it comes in discussions of quantization. If you look at if some of you are familiar with symplectic forms and so on, this thing comes, complex structures, this thing comes. Okay. So what is this? Well, UN leaves the following quadratic form invariant: Zi prime bar Zi invariant, right? It's from I equal to 1 to n. Okay. Because it is a unitary group. Now if I write Zi as real and imaginary part, what happens? This becomes simply xi squared plus yi squared. Okay, is just a real type scalar product in 2n dimensions. Now do the following. Okay. If u, which is an element of my un acting on z, okay, so u is n by n, so u is n by n, some matrix, z is acting on zn, is equal to say z1 prime up to zn prime. Separate real and imaginary parts, that is write Zi as xi plus iyi on this side. On this side z1 prime you write as xi prime plus yi prime. Then the way that remark, this implies that summation xi squared plus yi squared is equal to summation xi prime squared plus yi prime squared. By that remark there, and furthermore, okay, and the transformation is a 2n by 2n matrix for u. So I am going to get some 2n by 2n matrix, okay, which sends this x1 up to xn, y1 up to yn, okay, to this one x1 prime to xn prime, y1 prime up to yn prime, okay, is linear. Leaves the quadratic form invariant. It's a linear transformation, and clearly R is real. Because it is mapping a real vector to a real vector. So we conclude that this matrix Ru is living in SO2n. Right? Your question?
There's a very nice way to see this matrix. We're given the SU and the UN matrix. You take every matrix, which is a complex number, and you replace it by a 2 by 2 log.
I'm going to do that right now. Okay. So her remark, this which is this is quite explicit. That's also explicit, but more elegant, I would say. Okay. The idea is the following. You will see immediately that this the matrix, the point is the following. Okay. Role of, let me write chain remark, let me call it epsilon, this is our notation. You would have come across this object if you had done classical mechanics. Okay. This antisymmetric matrix. Okay. So epsilon is antisymmetric, epsilon is real, and epsilon squared is -1. Okay. Now look at I. Okay. This and so in fact what I want to say is this I here, the imaginary unit I, has a property that it is changing the sign. Okay. The reality is, then I squared is -1. the self-adjointness over reals. If I consider real objects, dagger becomes transpose, okay. So corresponds to anti-symmetry. And this is the of epsilon, and this corresponds to the fact that epsilon squared is -1. So this epsilon has all the properties of I. So following up G, what we do, for example, when people discuss how to quantize systems with a finite number of degrees of freedom, is we take this u in un, okay, and we write this as u plus u star over 2. So this is a u real plus I times u minus u star over 2i. This is the imaginary part of u. Of course, it is real. I mean, I have put out the I there, and you replace this by 1 2 cross 2 tensor UR. So this is now 2n by 2n matrix plus get rid of this epsilon 1 I by replacing by epsilon tensor UI. You agree with me, right? And this thing here is real, and you can check that it is in SO2n. This is the same as what we did by separating real and imaginary parts, but it looks nicer. It is nicer. And it brings in the role of this antisymmetry matrix, okay, which is what comes in canonical quantization. If you take the Poisson bracket of positions and momenta, you get this minus sign. Okay, minus QP, Poisson bracket is minus is 1. That antisymmetric matrix, PQ is -1. It is that thing that is coming here. Now I want to look at another example, Poincare group. P. I remind you what it is. Okay, consists of a translation and a Lorentz transformation with a product which is A prime plus lambda prime A lambda prime lambda. Okay. This is what I had done earlier, but one thing I forgot to say here last time was it has what is the I did not write the inverse of A lambda, which is good to know. Okay. What is the inverse of A lambda for this group? It is minus lambda inverse A, lambda inverse. You can check it. Okay. If I take this, multiply by A lambda, you get identity. The identity is simply 0 1. And in this group, there are two distinguished subgroups. So translations, let me call it T4, which consists of all translations of this kind, and Lorentz transformations, let me call it L, which will be all this thing with no zero translation and elements in lambda form subgroups. When we say Lorentz transformations, we always mean Lorentz transformations up to an isomorphism. We don't distinguish between groups which are isomorphic. Okay? Notice that this is not canonical. There are a lot of translation subgroups. Not only this, Can you tell me another one completely isomorphic to this T4, which won't look like this at all if you work it out, but within the Lorentz group, within the Poincare group? Can you guess? We sort of discussed it last time. Okay. I can take that one and conjugate it with the Lorentz transformation. Okay. So note, if I take T4 and I conjugate it 0 lambda inverse, since these things don't pass through T4, this will be isomorphic to T4. To translations, right? Yeah. Or likewise, we can, in fact, we can work it out. Well, this is easy, but I can do the other way also. If I take Lorentz transformations and I take any translation, A1 inverse is isomorphic to L. Right, because this is the inner conjugation. Last time we proved they argued that inner conjugation is an isomorphism, right? So this is an isomorphism. In this case, it is rather easy what it is. So in this case, A1, if I put these things, will become lambda A1. So it simply becomes a Lorentz transform translation. Okay. Here you will get a mess. If you do this, okay, you already for rotations, you take rotation and they translated rotations, okay, you will get some funny thing. Okay. But here you have both not only rotations but also Lorentz transformations, and they translate the Lorentz transformation. What happens? It looks very funny. In fact, it is very funny and causes difficulties in identifying what you mean by rotations in a moving frame, things of that kind. Okay. So anyway, this has to be kept in mind. Okay. So that brings me to this issue of cosets and invariant subgroups. Or normal subgroups. Let us look at first cosets. Left. These are ways of partitioning the group into disjoint sets. Okay. So if H is a subgroup, of G, okay, a left coset is GH. G is in G. So this is a left coset. A right coset is at G. What is their importance? Well, first, later when we look at groups acting on manifolds, for example, rotations acting on manifolds, our three-dimensional vector space rotation is acting. The action of your symmetry group on manifolds is completely can be classified, understood in terms of cosets. Okay, we will see that later, especially when we start doing continuous groups. The second is that when H has a certain property, this lets us gives us the notion of dividing a group by a subgroup. Okay, what corresponds to division of a group by a subgroup to get another group. Okay. So, we are also going in that direction when we are discussing this subject. Okay. So, what are the important properties here? Okay. If you want theorem, I kept saying that I have not understood the difference between theorem and lemma and what one more thing is there. Corollary, theorem, lemma, there is one more thing. Axiom, you know. Axiom is an assumption, you just dogma. Catholic dogma is replaced by axiom in mathematics, nothing more. So, there is one more thing, I forgot. Anyway, this theorem, this statement is the following. Okay. Let us consider it for left courses. First statement is two left courses are either totally disjoint or identical. So, what this means is GH is intersection G prime H for any G and G prime is either equal to GH, okay, or G prime H, okay. It is symmetric anyway, okay, or is null. Secondly, if an element G bar is in GH, then G bar H is equal to GH. I should have said at the beginning, okay, here, note, I should have said that G is union of GH, which is union of G at G. Call it, I'll tell you. Namely, the union of all the cosets gives all the elements of the group. That I should have said. Okay. But this is I am writing union. I don't know whether they are disjoint or not. But now, in fact, those unions are disjoint unions. And why is this case? Okay. Why is alpha true? Alpha is true for rather trivial reason. Because why? Why is alpha true? When I take the union, I get back odd members of the set.
All H's have E. So
all H has identity, no? So GH has G. So you are finished, right? Right? Because identity is in H. So you.
This B property is not really clear to me. How do you get this G bar term?
Take any element G bar from GH. GH is a set, no? Take anything and form a new coset. You will not get anything, you will get back the old one. As a set. Okay?
You are applying G bar again and again.
G bar, I am multiplying all elements of the group H, subgroup H. So this one will consist of, GH will consist of.
How is it equal to GH again? Okay, the right
Okay. So let us look at, so if you want to prove, okay, first we notice, okay, let me write A, okay, that G1, G2 belong to the same coset if and only if G1 inverse G2 belongs to H. Okay. Proof is rather easy. Why? For okay, if G1 G2 belongs to GH, then there exists H1 H2 such that G1 is GH1, G2 is GH2. Yes, by definition. So we see that the way I have written it. Okay, G1 inverse. Yeah, this implies G1 inverse G2. The G's cancel is H1 inverse H2, which belongs to H. Okay. Only if I should say, okay, if this is only if is also if G1 inverse G2 belongs to H, okay, we know that G1 inverse G2 is some H in H. Okay. What do I want to say? I want to say that if G1, they belong to the same coset. Okay. So G2 is G1H. So you see immediately that G2 belongs to G2H, okay, which is equal to G1HH, which is G1H, which contains G1. Okay. Yes. So two G's belong to the same left coset if and only if this condition is fulfilled. Okay. Now B. Okay. I want to prove that they are either totally disjoint or identical. So if G1H intersection G2H, okay, is not null, there is some common element. Okay. This is a common element with this. Okay. There exists Hi such that G1 H1 is equal to G2 H2. Right? There is some common element, there is some intersection, common element. So there is some H1 here and some H2 here. So this equation is fulfilled. So this is from here. Okay. This I want to show that these two implies G1H, which is G1 H1H, because H1H is which is G2 H2H, which is G2H. Yes, so they are identical. Yes, there is no intersection, nothing to prove. There is an intersection. There is one element in common. Then for that element, there is some H1 here and H2 here. I have this equation. So let me look at the cosets. I look at G1H, but small h1 multiplying this, there is nothing. So I write like this. But this is equal to this, so I write like this. Then I absorb back, I get this. So that is equal to this. So the cosets are identical. So what I have got here is a partitioning of the group into disjoint sets, right? So we have a partitioning of the group G into disjoint cosets, left cosets GH. Similarly for right cosets, there is no difference in the proof. This automatically tells you some very funny result, not obvious. I think it is due to Lagrange. Okay, before I do that, I also want to prove this part here. Finally, I want to prove this part here. How will I prove it? If G bar is in GH, I want to prove that G bar H is GH. Why? G bar H is either disjoint from GH or is identical, but it is not disjoint because this contains intersection of this contains G bar. Okay, this intersection contains right. This is set. This contains G bar because H has identity. This contains G bar by hypothesis. So these two cosets are not disjoint. So they have no chance. They are equal. This means that you can label the cosets by picking one element. So we can label the cosets left or right, okay, by picking one element each. Well, may or may not be possible. I mean, there may be. Okay, attention. How do this is side remark. Okay, but for finite case, no problem. Suppose you take G to be SU, say SO3. And I'll take my H to be rotations around third axis. So I have a coset. So I have this partitioning. So I have rotations around x axis, third axis. Then I multiply it by some another rotation, get something else, and so on. Now I try picking one element from each set. Okay. Claim from this set R H. Okay. This set. Okay. R is in SO3. It is impossible to pick one R from each of these things in a smooth way. Impossible to pick this is a side remark. some physical reason for me to say this. Okay, I'll come. 1 R each. Okay, from each coset. So this is equivalent to picking a unique rotation from third axis to any other direction. I'll come.
While you write in the last board, you make the writing a bit more bold,
Harder.
hard to read from here.
It's my fault, but I say today I heard the newspaper that you get weak if you are a vegetarian. Mr. Modi has declared that in Gujarat people are thin because they are vegetarians. So I am a vegetarian. So it creates problems. Okay? But you can ask me. I'll try my best. I am aware of my fault. It's not that I am not aware. So this is why did I say this? It is equivalent to saying that in third, to try take the two-dimensional sphere. So this is S2. You try to find one rotation which takes you from here to here. Okay, you try to pick from here some particular rotation, some Euler angles. So you take from here to here. Okay. You try doing it all over this sphere. Can you do it? Impossible. Okay. There are many ways of showing this. Okay. And this result is what leads you to magnetic monopause. By some strange imagination of Paul Dirac, this ends up by predicting that electric charge is quantized by something he wrote at the age of, I think, must have been 22 or 23. You have plenty of time. I mean, he wrote it. It was in 1931 that he wrote the paper. Okay. This is called this obstruction. This is the same statement that the polar and azimuthal coordinates theta phi cannot be parametrizing the two-dimensional sphere in a one-to-one way. Impossible. Because if it were, this is the same statement, all these statements are the same. Okay. Because if theta phi, the polar and azimuth, were giving a point of the sphere uniquely, the sphere will look like a square. What? No. This is the core of his argument. He doesn't say like this, but this is a core of his argument, which ends up by saying that electromagnetic monopause can exist in quantum theory in a 1931 paper, and nowadays we call it by various names like hopf vibration and stuff. Okay, but he did it in 1931. Yes.
Or the possibility of
Sorry.
Or the possibility of combing the sphere, because
Combing the sphere. Yes, the same. This is the same. If it were possible, you can see contradiction. The sphere look like a square. No? If you can produce theta and phi from 0 to pi and 0 to 2 pi, and uniquely way, the sphere should look like a square, but that is nonsense, no? Because sphere is not a square. Okay? So something is wrong. And the reason is that the coordination is singular, many to one at some point, necessarily. Sorry? Anyway, that is a side remark, but so there are this statement about cosets, labeling cosets by elements does not always work, and the most interesting cases are where it fails. Okay. So this happens quite routinely when you go in. Actually, it happens already in chemistry, many cases. Okay. But the chemists don't seem interested in this. In quantum field theory, it happens with great frequency. But we'll come back to this. Okay. A consequence. for finite groups, just as an aside, I think it's called Lagrange. Let G denote order G. This result is not at all obvious if you just look at it. I am going to say what Lagrange says. Then the order, the subgroup H divides the order G to give the number of cosets of left or right. You see the proof? It's counting proof. You just write yes. This is simply counting proof. For I can write G as disjoint union of GIH then count. Okay. Each of these things have an order. I am just multiplying H by so order is H. Because I am just taking H and multiplying each by G. The order here is G. It is disjoint union. So G better divide H and give you the number of cosets. So theorem of Lagrange. Yeah, I think Lagrange very simple but not obvious. You try to guess it without any understanding. It's one of these trick proofs, okay? Proof for all finite groups. Another thing I will state here, but you can think about it. A group order, a group of prime order is cyclic. What does it mean? That is, okay, these are the form identity Z some Z to the K, then Z to the K plus 1 is E. A group of prime order is cyclic. Not obvious, right? The reason is that you cannot have a subgroup. Okay, I will come to that. Okay, it's prime order. So prime is there is nothing which can divide it. Okay, so you have to play around with this a little bit, and then you get the answer. Okay. Okay. Now I want to look at a slight refinement of this concept. So we have discussed cosets. Okay. Now I give a definition. H is an invariant subgroup of G or normal if GH G inverse is H. That is, in this case, okay, left and right cosets are the same There is GH is Hg, okay, and we can write G over H as GH. This is a definition for Hg. They are all the same. The space of cosets, you don't have to distinguish left and right, so you can simply write like this. We will give many examples, but today I will want to finish by saying, before I elaborate on it next week, theorem G over H is a group under set multiplication. Okay. In this multiplication, H is the identity, and the inverse of GH is simply G inverse of H. Okay. So G over H is is a group, the factor group of G by H So, the proof is 2 lines, but we need to look at examples. For A, it's clear that G1H, G2H, here I am multiplying this set here by this set here, so I just multiply element by element, but G2 can pass through here, so it is G1, G2, HH. But HH is H as I said, so it is simply G1, G2H. So this is a multiplication law, and H is identity because GHH is simply GH, and finally the inverse GH, G inverse H is H, right? Because I can pass this through and multiply here, so get identity, so implying G inverse H. In the Poincare group, it will be practically impossible to say what is a Lorentz transformation. Okay? The whole thing will get mixed up. But in fact, what happens is that there is this invariant subgroup, namely the translations, which you can take out. Then you get the Lorentz group. Okay? Likewise, the group of Euclidean motions in a plane or in 3 dimensions, you can take out the translations which form an invariant subgroup, quotient it out, and you will get the rotation group. So this situation of invariant subgroups and factor groups is quite prevalent in quantum physics especially, and also plays a very important role in describing elementary particles. So we will come to these things in the next talk.